So today we'll be talking about theoretical issues, mostly associated with excess heat. To begin with, we consider theory versus experiment. Um, Experiment comes first. Experiment should come first. There are issues as to whether we believe a specific result, how to interpret a result, whether or not an experiment's reproducible. Theory comes second. And for this presentation, we will be taking it as given that the excess heat experiments in cold fusion are correct. Theory rests on foundations. People have done a lot of work previously, both experimental and theoretical. We would like, if possible, to build upon the foundation. These foundations include quantum mechanics, the standard model, QED, QCD, electroweak theory. Also, something called quantum hadrodynamics provides a foundation for the nucleon interaction in nuclear physics. So we would like not to dispense with quantum mechanics or dispense with QED or QCD as is sometimes done in our field. So what input from experiment do we assume in this talk? We will be focusing, as I mentioned, on excess heat, large magnitude, greater than chemical energy available. People don't measure commensurate chemical products and no commensurate energetic nuclear products. There is evidence for helium-4 in amounts commensurate with the energy produced. We definitely need more experiments that focus on helium-4 and the connection with the energy produced. Let's begin thinking about deuteron-deuteron fusion. It came about in connection with explanations of cold fusion back in 1989. For incoherent fusion, two deuterons, as in a deuteron molecule, can fuse incoherently to make 3+1 products, helium-3 plus neutron, proton plus a triton, or there can be gamma emission at low probability. Deuteron-deuteron fusion, incoherent fusion is, of course, well understood. To get the deuterons together, there's a Coulomb barrier. They're charged. We are not able to just arbitrarily decide to flip off the Coulomb barrier. I've got a calculation here of the probability amplitude associated with the D2 molecule. So up near the peak of the probability amplitude is the 0.74 angstrom separation associated with the molecule. But to get the deuterons closer together, they've got to tunnel through the Coulomb barrier. And as a result, the probability amplitude and the associated probability goes down. This is captured in terms of gamma factor, and in terms of numbers, works like this. The gamma factor is about 10 to the minus 35. There's also, to make sense of this, there's a volume factor. The molecule is big, the nucleus is small, and that comes into the problem as well. Screening, the Coulomb interaction can be screened as following experiments in the associated interpretation, basically at low energy. The ratio of the cross-section observed to what would be expected if there are no screening increases at lower energy, and that's consistent with the screening effect. The associated screening energy is perhaps 200 to 300 electron volts for palladium. And in this particular case, that would give us an enhancement on the order of 10 orders of magnitude, or a little bit more. So Coulomb barrier hinders fusion near room temperature. Screening can make a big difference. For molecule, we can increase the rate due to screening by perhaps 22 orders of magnitude or thereabouts. Incoherent fusion is far too slow to be observed near room temperature in cold fusion experiments. And if such reactions occurred, there would be energetic nuclear products which are not observed in amounts commensurate with the energy. People have talked about having tunneling of hydrogen or deuterium to higher Z nuclei. The Coulomb barrier is absolutely prohibited for this. Cold fusion is not due to incoherent DD fusion for the reasons given. Coherent processes. Why coherent processes? Well, because incoherent fusion or fission or nuclear reactions is a non-starter for theory, because energy and momentum conservation in connection with such reactions would give rise to energetic products commensurate with the energy produced. And that's just simply not observed in experiments. An example of a coherent process which is relevant would be excitation transfer. So in the case of excitation transfer, which is well known in atomic physics, biophysics, and other areas of physics, we might start with a nucleus that's excited, or an atom that's excited atomic state or molecular state, which interacts with another system that's in the ground state. And in connection with excitation transfer, the excitation is transferred from one system to the other. So that's what this diagram is all about. This was observed experimentally about a century ago and understood theoretically, basically within 10 years or so, qualitatively and quantitatively subsequently. There's no issue these days about excitation transfer. It's observed experimentally, understood theoretically, and it's a tool we can work with to address cold fusion issues. The idea for cold fusion is that if the excitation transfer involves a fusion system, like the D2 to helium-4 system here, then an excitation transfer process can move the excitation from the D2 down to the helium-4, and the 24 MeV energy would be moved elsewhere. So this is has been proposed for quite a while now in connection with cold fusion. An advantage of this is that the helium-4 ground state, due to its stability both as a nucleus and both as an atomic system in a trap, has is preferred as a product as opposed to the 3+1 system. Question is, what in the experiments, what's the helium-4 energy at birth? So the issue is, if we are trying to decide between coherent mechanisms and incoherent mechanisms, if we were able to measure the energy of a helium-4 nucleus when it was born, then we could tell the difference between a coherent, whether it's produced coherently or incoherently. If it's produced incoherently, for example, either through a helium-4 plus gamma mechanism or a helium-4 plus electron mechanism or helium-4 plus anything else mechanism, then the helium-4 nucleus would have energy. 76 keV in the case of gamma emission, and that's sufficient to bang into nearby deuterons and get DD fusion reactions. So you can, if you detect neutrons in connection with excess heat or during an excess heat experiment, you can get information as to how fast or how much energy the helium-4 nucleus has when it's born. There's a minor headache that getting appropriate charged particle detectors into electrochemical cell or other systems is not always easy to do. The brainstorm was to use the palladium deuteride itself as the detector, and then can be calculated theoretically for knock-on reactions. So then you can compare against experiment. Neutron emission is not time correlated with excess heat production in the Takahashi experiments. Evidence for anti-correlation. The 76 keV birth energy is not even on the graph here. It ends at 30 kilovolts. But the neutron emission that you would expect if the helium-4 had 76 keV initially would be 3 orders of magnitude higher than the lower limits observed in numerous experiments. So the conclusion is that helium-4 production is not through an incoherent process. Of course, we probably knew that by the absence of gammas in the first place, but people have pursued models where the gammas would somehow be eaten. Okay, so deuteron-deuteron fusion normally studies as an incoherent process, which is good for accelerator and hot fusion experiments and not good for cold fusion experiments. For cold fusion experiments, then excitation transfer is part of a bigger coherent process, in my view, is the only possibility. Active sites, where does this happen? So as people have strong opinions about this, let's think briefly about it. If we have bulk palladium deuteride, we have sodium chloride lattice structure, we have palladium at various sites and FCC lattice, we have the deuterium atoms are in octahedral sites, at least near room temperature. And in order to get 2 deuterons together, if you try to put 2 of them into a single octahedral site, they're not happy. It's energetically, well, it takes a lot of energy to do it. And near room temperature, you don't have the energy to do it. So the thought is that vacancy sites or defect sites is where things would happen. In the case of a monovacancy, one of the palladium nuclei can be missing, and then around a monovacancy, the equilibrium positions, if you have a small number of deuterons or deuterium atoms, it could be O sites, but it could equally be tetrahedral sites. They're nearly degenerate within a few millivolts around a vacancy, both in palladium deuteride or hydride and also nickel deuteride or hydride. So maximizing the number of vacancies seems to be an important thing to do if you're relying on vacancies. One way to do that is to construct a Fukai structure. So the idea is that the thermodynamics of the system favors having lots of vacancies near room temperature. The headache is that if you have a piece of palladium and you've loaded it with deuterium, the vacancies, the atomic self-diffusion is slow, so you tend not to be making very many. If your system is very highly stressed, or if it's very small, if it's a nanoscale system, then it's easier to have vacancies diffuse, or if you think about the host metal atoms diffuse. Another possibility, of course, is microcracks, which in my view basically work very similarly. There's no essential difference. The big issue is how many sites do you have in connection with your microcracks, or how many vacancies you make, or do you get a vacancy phase structure to work with. There is something special about palladium. So palladium as an atom combined with hydrogen to make PDH. It combined with 2 hydrogens to make PDH2 in a bunny ear configuration, sort of like H2O. But also palladium combined with molecular H2 or D2 for that matter, as a molecule, as a spherical molecule. This was not believed possible up to about 1980. Then theoretically it was shown that that the ground state would be this, and shortly thereafter experiments followed where this was observed. But for example, for the singlet A system, here is the energy minimum, and it corresponds to dihydrogen bonding to the palladium molecule, which again is very special. There's not very many atoms, metal atoms, that bind with H2 or D2 as a molecule. The idea is that if you bind it as a molecule, then the H2 or D2, they're closer together. So, for example, if you're hoping to get tunneling to occur, having them be close together is a good thing. Nickel hydrogen, nickel H2 almost works the same way. There's a minimum with a dihydrogen complex, but it's just that the bunny ear configuration has a little bit lower energy. We would expect around a vacancy or microcrack or in a Fukai phase that there would be isomerization of the various O site, T site occupation configurations, along with the D2 or H2 or HD spending time in dihydrogen complexes. So I think this is how the deuterons get together. We, of course, would like experimental confirmation. Monovacancies are detectable with neutron scattering. NMR is good for detecting H and D dihydrogen complexes. There are technical issues in metals, but in nanomaterial or powders or something, it's quite possible that such experiments could be done. It would be very useful in our field. Positron annihilation has been used primarily by Japanese groups for studying vacancies in fact, palladium hydride, palladium deuteride. There are questions: does fast co-deposition produce high defects or vacancies? Namely, if you do the LETS co-deposition protocol and then use positron annihilation, will you find a lot of vacancies? A question I've been curious about forever is, do the nanoparticles, for example, used by Japanese group, Mitchell Swartz and others, do they have lots of vacancies? And finally, is there actually a correlation between vacancies, defects, microcracks, and excess heat production? Do you get more excess heat in samples that have more of these sites? Enhancement factors. Okay, so we're going to try to do theory. Then the first thing we run into is that nuclei are very small, which means that coupling matrix elements involving electric fields or magnetic fields or other interactions are small. The associated dynamics out of the box you would expect to be too slow to be relevant. And this would be especially so if you have D2 fusing to make helium-4, where you have a Coulomb barrier and the gamma factor is very small. So without enhancement factors, you would not expect to see anything. Enhancement factors are known and they're important. They're known in, quote, classical physics, where antennas radiating in phase will radiate more power. If you think of an atom or a molecule as a little antenna in connection with radiation, then radiative decay will be accelerated due to such enhancement factors if they're close. The math is simpler if they're well within a wavelength, or if all the systems interact identically with the fields or whatever systems that you're interacting with. So if we're going to have anomalies, we need to have interactions with the nuclei sort of be uniform with the interactions between individual nuclei have to be uniform with a common extended quantum system or a field. For example, a large oscillatory magnetic field would give rise to Dicke factors, low frequency acoustic phonons, terahertz phonons in the presence of phonon gain, where the terahertz phonons are special points, where all the nuclei are doing the same thing at the different sites. Low frequency spin waves can interact in this way. And plasmons can also work this way. There's a minor headache that the decay rate's very fast, but if you sustain them, like with a laser or something, then they have the possibility of participating this way. I'm of the opinion that for many of the Fleisch and Pons experiments with excess heat, the vibrations, lattice vibrations are the mode. The acoustic modes, of course, can be delocalized over a very large number of nuclear sites. Again, optical phonons, I think, in practice play a role. I think because the coherence length is very small, there has to be phonon gain in order for there to be coherence over an extended volume. So how to think about it? So I'm thinking vibrations interact with lots of nuclei. We get Dickey factors. The equations associated with the models, at least that I've been looking at, are sort of like the equations you get for light amplification laser. So if you think about it, you put in some light, you get more light out for laser amplifier. If you don't put any light, then perhaps you wouldn't see much out, except that the amplifier itself generates some light, so you will get some out. But you would get more out in an amplifier if you put some in initially. An amplifier is an amplifier after all. So the idea is for excess heat production, you need a source of vibrations, typically optical phonons, to get things kicked off. Now, once they get going, and once you've got some amplification going on, if you've got feedback, so in a laser, if you've got mirrors, the light goes back and forth and back and forth. So it kind of, you no longer have to kick some in because the light from the last pass after hitting a reflection can come back through. So for excess heat, the idea is if it's working really well, you should only need to put some phonons in initially to kick things off, but then subsequently it should be able to sustain itself. So the LETS to laser experiments like that. I note the Google supported negative result, and I note that LETS had argued that there was an error in the procedure used for the samples. Apparently, this is not widely known, but it's an important issue. Let's think about transmutation briefly. So many of the transmutation observations involve new nuclei that are lower mass than the host lattice. And under these conditions, you can think of a fission type mechanism as being relevant. The Iowa experiment and a few other experiments involves the apparent creation of heavier nuclei, so a different mechanism would be involved. We've commented on that in the past. So for this to work, there's no particular problem. You need some energy to help get through the Coulomb barrier. Basically, most heavy nuclei are unstable to fission decay. But the headache is that the tunneling rates are very slow. But if you add some energy, it can happen faster. Now, if you're putting in energy into nuclear systems from excitation transfer from fusion reaction, then you have energy inside of these nuclear systems that could easily be a source for making fission occur to make transmutation products. The only question is tunneling rates, energy, and what specific states are involved. I will be talking more about this during my presentation during the conference. Let's think a little bit about modeling. So the idea is that there's been an awful lot of modeling done for an awful lot of systems previously, especially coherent systems. And what we'd like to do is to make use of standard models where they're available. So the approach I've been taking recently, start with a physical picture, assemble a Hamiltonian for the coherent part of the dynamics, can use Ehrenfest's theorem or equivalent to get evolution equations, and then we can add loss to make a more realistic system. Let me go through a sort of an example of how this might work. We might start with a simple picture. So the simple picture would be D2 and helium-4 as the fusion system to start with, and then various reasonably stable nuclei with excited states that are sort of in a relevant energy regime. So the idea is we start with the excitation. In the fusion system, we use excitation transfer to move it into the into stable states of atomic nuclei, and then more of this, and then each time energy gets coupled to the vibrations, and we go down until we've basically reduced the nuclear energy to vibrational energy. So Hamiltonian, to describe this, we need Hamiltonian for the phonons, which would look like this in general and can be simplified if we've only got one phonon mode. Fusion system, which in the case of D2 to helium-4, might involve 4 relative kinetic energies and various nuclear and Coulomb potentials between the different nucleons. We could use a reduced finite basis approximation type model, or we could use an even simpler Dickey model for this. And same thing for the nuclear system. We've got a relative nuclear Hamiltonian, or we can work with a finite basis approximation, or we can use a Dickey approximation. And for transitions, if we've got D dot E coupling, we could also have mu dot B coupling, and there are other couplings available. Then we can do it ab initio. We can work with our finite basis system, or we can work with the Dickey system. So out of the box, this model has problems that the excitation transfer upon which all of this is based suffers from destructive interference. The second order excitation transfer doesn't depend on vibrational amplitudes, which means there's no delocalization, no Dickey factors, no coherent enhancements, and out of the box, it doesn't work. On the other hand, if we include more physics, we know that there's energy shifts off of resonance. So for example, for excitation transfer, if we have an initial state here and a final state, the transfer goes through intermediate states, which involve 2 excitations or 2 de-excitations, which are off of resonance. And if you're on the top one, it takes more energy to be here than the energy that you've got. And so the nucleon-nucleon potential is weaker here, and it's stronger down here for the states below. So if we include this, then excitation transfer is greatly enhanced. It now depends on vibrations, and coherence over a large volume is possible. So now we can put together a model which might look like this. So these guys raise and lower the nuclear states. These factors here deal with the excitation transfer. Here's the gamma factor and volume factors associated with the fusion. And these phi sub fj terms, these are hindrance factors associated with the phonon exchange. Basically, you need to have lots of phonons to exchange between the nuclei and the lattice. And if you don't have enough, then these factors are 0, and it says nothing happens whatsoever. So we can have models. We can develop dynamical equations. We might start with Ehrenfest equations and then adapt a classical version of them to look something like this. These kinds of dynamical equations are well known in magnetism and in various coherent dynamics models. And we can solve them and they do what you'd like. So for example, um, the pseudospin vector, the Z component is high, which means we have a lot of D2, and it goes down and it's all helium-4 here. And these guys are excitations of the stable nuclear state. So they're all in the ground state here, and then they get promoted to excited states. This is the first one, the second one, third one, fourth one. So basically, the energy is going downhill. The nuclear energy is going downhill in time here. So this is a toy model that sort of gives you an idea of sort of how it works. Then we can add loss to both the nuclear systems in case there's radiative decay or internal conversion, and we can add loss to the phonon system as well. Now, sadly, I mean, this kind of model is what we've been thinking about for years. And sadly, the headache is that excited nuclear states with a lot of energy, they're pretty unstable. And so it's difficult to identify exactly which ones are involved. So for example, for the HD excitation, the fusion energy is up here. And these are the states that are known in the NuDat2 nuclear energy or nuclear database. So there's plenty of nuclear states. However, not much is known about how stable they are. Most of them are unstable. In fact, exceedingly unstable, far too unstable for us to do what we need. So this has prevented us from getting realistic models. The physics of these models, the foundations are good, the physics is good, these models can do the kinds of things we need. The headache is to figure out which states are involved. And there's been some recent progress earlier this year, which may provide a very fundamental solution to this. So stay tuned. I'll be talking about this in my presentation at the conference. Thank you for your attention.